Okay, today I want to talk a little bit about spontaneous reactions and kind of the different factors that go into whether or not a chemical process is going to occur spontaneously or not. And by spontaneous, I mean that it's occurring without any outside influence. And by influence here, this is kind of a catch-all term that summarizes a whole bunch of things, and we'll kind of get into the different factors here, but it's all energy related. So without any outside energy influence, is the reaction going to occur spontaneously or not? If it's non-spontaneous, then it requires some sort of outside energy to occur. That's not to say it won't happen. It just won't happen without some sort of crutch here. And with spontaneous reactions, we think of spontaneous, and when I'm using the term spontaneous, like in common speech, I'd say, oh, I spontaneously went out and grabbed a margarita with friends. Well, yeah, that sounds like I just went out and bought a margarita, right? But with spontaneous reactions, it's spontaneous meaning that it's going to travel in that direction that it's written. It's going to travel in that forward direction. But the time scale on that doesn't mean it's necessarily happening right that second. We think of spontaneity as something happening in the moment. But for a chemical reaction, it just means that the process is going to occur without any outside energy being added. This could be on a very, very slow, like geologic time kind of slow time scale. And so my catchphrase always is that spontaneous does not mean instantaneous. So spontaneous does not mean instantaneous. And the first year that I taught general chemistry, which was about 3,000 years ago, my students got so sick of me here because I said that, that was my line. Spontaneous doesn't mean instantaneous. That's a U, believe it or not. And I was like, someone should put that on a bumper sticker. And so they made me a bumper sticker, which I think is awesome. So spontaneous does not mean instantaneous. So this is my go-to for this chapter, is that spontaneous doesn't mean instantaneous, but we can predict whether or not a reaction is going to occur without any outside influences. When you talk about chemical kinetics and the rates of chemical reactions, we've talked about things that can increase the speed of a process. So I can make them happen faster. I can add a catalyst. I can change the concentrations of things. So I can make a reaction occur more quickly, right? And that kind of goes back to collision theory as well. But is it going to happen in and of itself? That's that measure of spontaneity in a reaction. And so I want to talk about some of the factors that go into whether or not a reaction is going to be spontaneous or not. So let's talk about 3 factors. And then in future videos, we'll get into the details of some of them a little bit more. So one of the things that you've probably already seen is enthalpy. And that's that heat of the reaction at H. So enthalpy, and looking at the change in enthalpy in a chemical reaction, is going to give you an indication of whether or not that reaction is going to be spontaneous. So again, we care about the change in H because H, enthalpy, is a state function. So it's just, this is the state of affairs of the current situation, right? It's got some internal energy, there's some pressure and volume in there. So kind of what's the status of things? Well, how does that change going from reactants to products? That's sort of interesting for chemists. So we said if delta H is negative, then it's exothermic, meaning that the products are lower energy than the reactants, right? So we start off at a higher energy, we end up at lower energy. Things like to be lower energy, that's a good thing. So we end up with a negative delta H. It's an exothermic process. If delta H is positive, then we say it's endothermic. So we'd put energy in, and remember these terms too. This could be exergonic or endogonic. I prefer thermic because of the thermal, which means heat, right? So heat exiting, heat required, heat coming in. This is an O. Okay, so if I have a positive delta H, that means I had to add energy into the system. Now, if we go back to my definitions of spontaneous then, spontaneous versus non-spontaneous, if I'm just thinking about enthalpy and the change in enthalpy going from reactants to products, and I'm not thinking about any other factor, which one of these would be a spontaneous process? And hopefully you're thinking, okay, well, nature and the universe likes to go to the lowest energy possible. That's a good thing. If I had to put energy in, then that means I had to put in some sort of outside energy in order for this to occur. So it seems like this delta H being negative is a good thing for a spontaneous reaction. And that's true. An exothermic process is going to be a spontaneous process with no other factors involved, right? Because we have something that's higher energy, it's going to lower energy. There's that natural drive towards wanting to be at the ground state that's possible. So this in and of itself would lead to a spontaneous process. And it's kind of right in the definition here that an endothermic reaction, because it requires energy, is going to be non-spontaneous. Oh man, my handwriting is atrocious today. I apologize. I blame it on Thursday. It's a Thursday, I think. We'll see about that. Okay, so enthalpy, that's the energy of the chemical reaction. It's going to be spontaneous if it's negative. So we're thinking exothermic reactions there are the ones that are going to be energetically favorable if we're thinking about spontaneous processes. Now, the second factor that we want to talk about with spontaneous reactions is temperature. So we know, because we've talked about this in a number of different contexts, we know that temperature influences the speed of a chemical reaction. And when you increase the temperature, then you increase the speed of whichever process is going to require that temperature in order to speed up, right? So it's kind of a counterbalance. If we're thinking about Le Chatelier's principle, then how would the temperature impact things? Well, it depends if it's an endothermic or exothermic process. And kind of here's where the layers of complexity build on each other. Because if I'm just looking at enthalpy, then just in and of itself, is it exothermic or endothermic, gives me information about whether or not it's spontaneous or non-spontaneous. But with temperature as a factor, when I start tweaking temperature, that's going to impact each of these reaction types in different ways. So temperature has an impact on spontaneity. It can either make things spontaneous, it can make things less spontaneous. It has an impact, and there's lots of ways that happens, but kind of it all comes down to that collision theory, that if I increase the temperature, or kinetic molecular theory, then I increase the speed and the motion of particles, which increases the collisions. And we know that collisions cause chemistry, which increases the rate of the process. Now, again, that's all dependent on the type of reaction, because it's going to increase the speed of an endothermic process in a different way than it would for an exothermic process. So temperature is going to be one of those kind of wild card variables that it's going to have to factor in. It matters, but it's going to matter in different ways, kind of depending on whether it's increasing, decreasing, and the reaction type itself. And we'll get into that in later videos, but I just wanted to draw your attention to it as we're talking about factors that influence spontaneity. Okay, so the third factor I want to talk about is entropy. And I just got a chill even just saying it. I love entropy. Entropy is one of my favorite things to talk about. Entropy is the measure of disorder in the universe, and systems really like entropy, right? It's kind of a measure of chaos or disorder. And so we associate entropy with chaos because it's really about the measurement of how dispersed matter is. We know that matter likes to be spread out. Given, a room, and if I was to open a tank of gas, the gas particles aren't going to stay next to my gas tank. They're going to spread out, and they're going to disperse. And that measurement of how dispersed they are is a measurement of how low energy they are, right? Because it likes to be dispersed. And when we say that chemical things like this, or they favor this, or they're going to shift in this direction, then that's all to balance out the energy of things. It's all coming down to energy and the lowest energy possible. So I love entropy, and I love talking about energy and kind of the energy of moving particles. And so it's really important. So entropy, again, I'll spend a little more time on entropy in later videos. Entropy is S. That's the variable. I'm not sure where that comes from. That would be an interesting study. And again, because we're chemists, we're looking at the change in entropy going from one side of a chemical process to another. So usually we're thinking kind of a reactants to products kind of thing, right? Reactants to products. This is my chemical process. So I have an entropy that's associated with each of these. There's a measure of disorder of my reactants. So kind of this has to do with things like the phases of matter. And if we think about like a gas compared to a solid, which one would have a greater degree of disorder, then hopefully intuitively you say, well, obviously a gas has a greater degree of disorder, right? So there's a greater entropy associated with it. A solid as a solid versus a solid is in a solution, right? The solution would have more degree of disorder because of the dissociation of those particles in solution. So the phases of matter are going to matter. And then also the energy of the bonds too, kind of how things are connected together gives you an indication of the entropy. Okay, so kind of how tightly bound is everything together, and kind of the energy of those chemical bonds gives us information about the disorder of those chemical bonds. So the more ordered things are, then the less happy they are, which just fits with my entire life view, really. So we care about the entropy on one side, the entropy on the other, but the difference between it is sort of the more interesting quantity. So we look at delta S in the same way that we looked at delta H, our enthalpy change up there. So the change in the entropy is going to give us information about how favorable it is. If delta S is positive, okay, that's final minus initial, products minus reactants, then that means that I have a greater degree of entropy in my products than my reactants. So if delta S is positive, we're going towards more disordered states. I'm just going to say towards chaos, which is a little bit of an overstatement, but chemists, we make ourselves laugh. All right, and if I have a delta S that's negative, then that's going towards more order or less disorder, if you want to think about it that way. That's a couple negatives there. So I always think about this as a change in entropy. When it's positive, that's a positive thing. That's a good thing. It's going towards a more disordered state. And so for the reaction, that's a positive thing. If delta S is negative, that means I'm creating more order. And again, we'll get into the details of that in a future video. But that's going to not be a good thing. It's a negative thing for the system that we're looking at. So a positive delta S leading towards more disorder is going to lead us towards a spontaneous process. And again, sort of like with our enthalpy, this would be independent of other things, right? So we have all of these factors. We have enthalpy, we have temperature, and now we have entropy that are giving us information about the spontaneity or the non-spontaneity of a process. And when you put them all together in various combinations, right, because I could have a negative delta H, which is a good thing, but I could also have a negative delta S, which is a bad thing. So then that means that the temperature might have more of an impact, or what I'm looking at might have more of an impact. Or I could have a negative, I could have a delta H that's positive and a delta S that's negative. I have two negative things, but I can still make the reaction occur if I have the right conditions, if I have the right temperature conditions. And so figuring out what those are and tweaking those are going to give us information about kind of how to make chemical reactions happen or not happen, depending on what we're wanting to do. And it's all about whether or not they're spontaneous. Not instantaneous, but spontaneous.